Okay, I'm going to go ahead and start. Okay, we have been looking at the structure and synthesis of alcohols. I'm going to briefly review what we went over last time. These were new methods of preparing alcohols. There we go. All right, if we have a carbonyl compound, for example, I'll choose acetone. All right, one of the nucleophiles that we can add to this to make an alcohol would be an acetylide. Okay, and then this we would get from propine and NaNH2, which would remove that proton. Okay, this attacks the carbonyl carbon. Then in a separate step, we add dilute acid. Right, so to name this, longest chain would be 1, 2, 3, 4, 5. So that's pent. We want to give the alcohol the lowest number, and so this would be 2-all. And I'm going this way, 1, 2, 3. That would be pent 3-ine 2-all. We can also use Grignard's or organolithium reagents. All right, here's phenyl magnesium bromide. Okay, carbonyl is polarized, carbon end is plus. Nucleophile, which is this carbon, will attack the carbon nucleus. So we form a new bond right here. And then once this reaction is complete, Again, we add dilute acid. Okay, so this would be 2-phenyl propan 2-ol. Okay, if I used phenyl lithium, it would be exactly the same reaction. Okay, some of the limitations of Grignard reagents, we'll come back to esters and acid chlorides. Okay, some of the limitations include we have to be very careful to exclude water. None of our compounds can contain any of these acidic hydrogens, OH, NH, SH, or terminal alkyne. Okay, they also, you also have to avoid other carbonyls, nitriles, SO double bonds, or NO double bonds, unless the carbonyl or the nitrile is something you want to add to. Okay, the difference here with esters and acid chlorides. Okay, let me let urine in. Whoops. Oh, there he is. Okay. Okay, the difference with between aldehydes and ketones and acid chlorides and esters is that acid chlorides and esters can add 2 equivalents of Grignard. And the only difference is the leaving group. Okay, so for an ester, I'll just say methyl acetate, and we're using ethyl magnesium bromide. This adds to the carbonyl the same way. So we form this new carbon-carbon, whoops, new carbon-carbon bond. Okay, then what happens is that oxygen pushes down and it pushes out OCH3 minus. Okay, now we've got a ketone, and the ketone can react with the second equivalent. So this gives us and then, of course, we protonate it then. So we've added 2 ethyl groups. Okay, our longest chain now is 1, 2, 3, 4, 5. And so this would be 3-methyl pentan 3-ol. Okay, we don't protonate it at this step. Okay, this compound is not stable. We'll talk about that next semester. This is called the hemiacetal. Most hemiacetals are not stable. So this is going to go on to the ketone, and then the ketone accepts a second equivalent. Okay, if we have ethylene oxide, we can add a Grignard. That opens up the ring, and we get a primary alcohol 2 carbons longer than what we started with. Okay, if we have a substituted ethylene oxide, okay, something like this. Okay, the Grignard is a strong nucleophile. It will attack the less substituted side. Okay, so this is determined by the rate. Okay, this side is more acceptable, accessible, less crowded, and more easily attacked. Okay, this is just this is not a method of making alcohols, but this is included because it's under the theme of organometallic reagents. Okay, the main thing I want to emphasize here is that this is a lithium dialkyl cuprate, but only one of these alkyls is going to add. Okay, this is a way of coupling 2 groups together to make an alkane, or could also be an alkene, but only one of these R groups reacts. Okay, the other one stays with the copper. I want to review reductions of carbonyls. Okay, these are the 2 hydride reducing agents. Sodium borohydride just reduces aldehydes and ketones. Aldehydes go to primary alcohols, ketones go to secondary alcohols. Okay, this is the mechanism. It's just like the Grignard, except our nucleophile is the hydride. Okay, so hydride adds, and then this can actually be done in water or alcohol as a solvent, and then the alkoxide picks up an H from the solvent, and we get an alcohol. Okay, these are a couple of examples of sodium borohydride reductions. Lithium aluminum hydride is a stronger reducing agent. Okay, in this case, okay, notice the difference here. We can't use water as the solvent. We can't use alcohols as the solvent. We have to use something like ether or hexane. Okay, because lithium aluminum hydride reacts with anything that has an acidic hydrogen. Okay, this can be used not only with aldehydes and ketones, but also with esters and carboxylic acids. Okay, so in this first example, we have a ketone over here, we have an ester. Sodium borohydride only reduces the ketone. Okay, leaves the ester alone. Lithium aluminum hydride reduces the ketone and the ester. Okay, the ester will form a primary alcohol. Okay, and then the OCH3 will end up as methanol, so there'll be methanol out here. Catalytic hydrogenation with Raney nickel can produce alcohols from aldehydes and ketones. Okay, this doesn't work with carboxylic acids or esters. Raney nickel also reduces alkene groups and alkyne groups. Oops, let's back up. Okay, so here's a comparison. We have a compound with both an aldehyde and an alkene. Raney nickel adds hydrogen to both of those groups. We get this fully saturated compound. Sodium borohydride just attacks the aldehyde, and notice here it leaves the alkene alone. All right, our next topic is thiols or mercaptans. Mercaptans is the older term. These are the sulfur analogs of alcohols. Sulfur and oxygen are in the same family. The SH group is called a mercapto group. In the IUPAC, the suffix for a thiol is thiol. Okay, so here are some examples. The first one is methane thiol. Right, that's the IUPAC. The older name is methyl mercaptan. The one in the middle is butane 1-thiol. We do need the 1 because we could also have butane 2-thiol. Or N-butyl mercaptan is the older name or the common name. Alcohols in the IUPAC take precedence over thiols. And if a thiol is not the dominant functional group, then it's a mercapto. Okay, so this compound is 2-mercaptoethanol. Okay, some of you might have used this reagent in the lab in molecular biology or cell biology. Okay, one notable feature of thiols is they are several times more acidic than alcohols. Okay, so here is ethane thiol. It has a pKa of 10.5, and phenol, which we saw earlier in the chapter, has a pKa of about 10. Ethanol is about 15.9. Okay, so this is 6 pKa units, or about 1,000,000 times more acidic than ethanol. Okay, so we can, well, deprotonating ethanol with hydroxide doesn't work very well. With ethane thiol, we can readily deprotonate it because water is now 15.7. That's a weaker acid. Okay, so this goes to product. Okay, the explanation usually given is that sulfur, being a larger atom, more polarizable, can more easily spread that negative charge around its electron cloud. Right, thiophenol, also called benzene thiol, is even more acidic. It's about 7.8. And likewise, it can be deprotonated. thiophenol is 7.8, phenol is about 10. And, okay, so here we have resonance stabilizing this conjugate base, this anion. Okay, so thiols are more acidic than alcohols. They are not as acidic as carboxylic acids, which we'll talk about next semester. Okay, thiols can be synthesized from alkyl halides using sodium hydrosulfide. This is an SN2 reaction. If we do this in basic solution, this thiol can get deprotonated, and we have RS minus, which could then attack an alkyl halide. So we can get sulfides as a byproduct. Okay, so to prevent a second alkylation, use a large excess of sodium hydrosulfide with the alkyl halide. Okay, sulfide is the sulfur equivalent of an ether. Okay, so RSR. Okay, thiols have some reactions that are unique, and we don't have anything analogous for oxygen. Okay, this is one such reaction, and that's mild oxidation of thiols. Okay, this forms a disulfide. Okay, over here we have carbon, sulfur, sulfur, carbon. That's a disulfide. And that's in contrast to a peroxide, which is ROOR. Peroxides are unstable, they're explosive, they just takes a little bit of heat or light or mechanical shock to decompose peroxides. These are stable though. The reaction is reversible. Okay, it doesn't specify here how this is being oxidized or reduced. In biological systems, this is done enzymatically. Cysteine is one of the amino acids. And this is an important reaction in forming three-dimensional structures of proteins. Okay, if we have some kind of a globular protein, okay, one of the ways that it holds its three-dimensional shape is to form these disulfide bonds. Okay, there's other ways like hydrogen bonding and so on, but this is actually a covalent bond. Okay, I want to say some other things about thiols. Okay, let's start with this. Okay, the oxidation of thiols to disulfides and reduction of disulfides to thiols is reversible, and it's actually this reaction that is used in the permanent waving of hair. Okay, hair contains a protein called keratin. Keratin is rich in disulfide bonds. And so a reducing agent, usually something like thioglycolic acid, a reducing agent is used to break some of the disulfide bonds. Okay, and you can control to some extent how many are broken by the time of exposure. Okay, so in the beauty industry, I think this is called softening. Okay, you add this reducing agent, you break some of the disulfide bonds. Okay, then the hair is either straightened or set on rollers. And then a fixer, they call this a fixer, which is the oxidation. They use dilute hydrogen peroxide as an oxidizer. Okay, that reforms disulfide bonds, but the disulfide bonds are not in their original locations. Okay, so this imparts what we call a permanent wave to the hair. Okay. All right, backing up. Okay, one very notable property of thiols is that many of them have really strong, unpleasant odors. Methane thiol is a gas at room temperature. Okay, unlike methanol, it doesn't hydrogen bond. Okay, sulfur is not nearly as electronegative as oxygen. So it's a gas. And like hydrogen sulfide, H2S, it smells like rotten eggs. Ethane thiol or in the oil and gas industry, they call this ethyl mercaptan. Okay, traces of this are actually added to natural gas. Okay, and the reason is so you can smell a gas leak. And the concentration of this is really small. It might be, I'm going to say parts per trillion. Okay, but we can, most of us can smell that gas leak. It has, again, kind of a rotten egg odor. Okay, natural gas by itself doesn't have an odor, and so this enables us to detect a gas leak. All right, this compound in the middle, butane 1-thiol, okay, along with trans-butene 1-thiol, trans-butene 1-thiol. These are both present in skunk scent. These are both oily liquids, have a really strong odor. There are some other components as well. These are two of the main components. Okay, in your textbook, at the end of the chapter, one of the problems talks about remedying the skunk scent. For example, if your dog has been sprayed by a skunk, okay, what do you do? Okay, they used to say use tomato juice, but all that does is simply cover up the odor. It doesn't really get to the source of the odor. And so the remedy for skunk spray is a combination of, use a combination of sodium bicarbonate, baking soda, hydrogen peroxide, and vinyl detergent. Okay, the hydrogen peroxide will oxidize thiols to disulfides, and these will be easily emulsified with the detergent. The sodium bicarbonate will deprotonate the thiols, give you the ionic conjugate base, which will be more water soluble, more easily washed away. Right, thiols are also present in a number of plant sources. Okay, think about foods that have strong odors. Okay, garlic, onions. Okay, these, a lot of their odor comes from organic sulfur compounds. Right, I've been talking about unpleasant smelling thiols. This is one that, in particular, this is one that I find pleasant. This is a compound that is released when coffee is freshly brewed. Okay, so this gives the aroma of freshly brewed coffee, along with some other compounds, but this is one of the main odor components. Right, the name mercaptan comes from mercury capture. Okay, so thiols form strong bonds with mercury 2 ions and precipitate mercury. They also can form some bonds with some other metals. One of these is, one of them is called, let's see if I get this right. Okay, this is a compound, it's called British anti-lewisite, or BAL. Okay, during World War II, the Germans developed a poison gas called lewisite, and it contained arsenic. And the sulfur groups would bind very tightly to the arsenic and render it less toxic and less volatile. Okay, besides mild oxidation, okay, if you use a strong oxidizer, okay, a strong oxidizer would be something like KMNO4. In this case, you would go all the way to a sulfonic acid. Sulfonic acids are something we're going to talk about next semester as well. And again, there's no equivalent with oxygen. Oxygen cannot have this many bonds. Okay, so there's a few differences between thiols and alcohols. Right, then I'm going to open up another tab here. Canvas. Okay. Okay, right now, that was chapter 10. I'm going to open up chapter 11. We'll just get started on this. Okay, chapters 12 and 13. Scroll down here. So that's chapter 11. Okay, actually, I wanted to. Chapter 11 is reactions of alcohols. Chapters 12 and 13 we're going to cover in lab. Both those chapters deal with identification, qualitative analysis of organic compounds using spectroscopy to identify compounds. Okay, and then I'm anticipating, okay, so 12 and 13 we'll cover in lab. Chapter 14 is a fairly short chapter. It's on ethers. So I'm anticipating that we'll end with chapter 14 for the semester.
So for the following lecture classes, what will we be doing?
We will, okay, so the next 2 or 3 lectures will be on chapter 11. And then I'm going to have some practice drills like we did with the alkenes chapter. And then 12 and 13, those are going to be pre-recorded.
Okay.
Those will be with lab, and I'll have some assignments with those. And then chapter 14 will be, I'm anticipating that's as far as we'll go. Okay. Okay, so this involves starting with alcohols and converting them into other compounds. Okay, here is, this compound is called isopentyl acetate. This is one we often make in the lab. Okay, this is the alarm pheromone for the honeybee. Okay, so what are some of the things that we can do with alcohols? Right, we can dehydrate them to alkenes. Okay, we've seen that one in lab. We dehydrated cyclohexanol to cyclohexene using sulfuric or phosphoric acid. Okay, in the previous chapter, we talked about reducing aldehydes or ketones to alcohols. We can go the other way. We can oxidize primary or secondary alcohols to aldehydes or ketones. We can form alkyl halides. Okay, we've done a couple of those, 1-bromobutane, T-butyl chloride. We'll look at some other methods of converting alcohols to alkyl halides. We'll talk about reduction to alkanes. Okay, if you convert an alcohol to an alkane, that is a reduction because you're reducing the oxygen content. Okay, esterification, making an ester from an alcohol. Tosylation, and then Williamson ether synthesis. Okay, so here is the summary table. Okay, so we can dehydrate. Okay, as long as there's a hydrogen on the carbon next to this carbon, we can dehydrate to form an alkene. We can oxidize to ketones, aldehydes, or carboxylic acids. Okay, we can do a substitution. Okay, we did 2 of those in lab. We can reduce an alcohol to an alkane. Okay, there's various reagents. In this particular chapter, we'll talk about using carboxylic acids with alcohols to form esters. And we'll talk about converting alcohols to what are called tosylates. The tosylate is actually a type of ester. And okay, there's a hint here why we do that. OH is really a poor leaving group, but tosylate's a good leaving group. So now we can do a lot more substitution reactions with the tosylate. Okay, we can also use alcohols to make ethers. Okay. All right, so I'm going to go ahead and stop here, and I'll see you virtually on Friday. Okay, next week is all virtual. No class on Wednesday because that is a holiday. Okay, so I will see you tomorrow in lab.